Hello everyone, welcome to We Learn Tutorials. In this video, we are going to do periodic classification of elements. This is chapter 5 of NCERT class 10th. So let's start. Before starting with the concept, let us understand why do we need periodic table. For this, you just have to look at the examples given below. In the first example, here if you see this is unorganized pile of books. Here if I say just get me maths book or science book, it will be very difficult for you to find it out. But here see all the books are arranged systematically. Here might be chemistry books, here mathematics books, physics books, English books, so like this. So it will be much easier for you to get any required book. Moreover, if you go to any grocery store or vegetable store, you can see all the similar items. Here also you can see all similar items, they are placed together. So why these items they are placed together? See, the only reason is that so that you can easily find out the required things. So whatever you need, you can find it easily. Same way, there is a need of periodic table. See, there are 118 elements known today. So in order to find or in order to study different elements, there should be some similarity or systematic arrangement of the elements so that you can study it properly or easily. That's why. So one example, we'll come to that later. Then before that, let us discuss one example. See, this example, it's given in your textbook. See here, imagine you and your friends have found a pieces of an old map to reach a treasure. So you just have found a pieces of old map. Would it be easy or chaotic to find the way to the treasure? See, it won't be easy because only pieces of maps are there. See, pieces are unarranged. Only if you arrange these pieces, then it will be much easier for you to find the way to the treasure. So similarly, chaos were there in chemistry as elements were known, but there was no clue as to how to classify and study about them. So we can see so many elements were there, but it was very difficult to classify them whether these are metals or non-metals or other different properties also, and also how to study them. So that's why there is a need of periodic table so that all the similar type of or all the elements which have similar properties, they can be grouped together, and while studying also it would be much easier. So let's see now. See, at present 118 elements are known to us and all of these have different properties. Out of these 118, only 94 elements are naturally occurring. So scientists, they were looking for some pattern in their properties on the basis of which they can study such a large number of elements with ease. Like if you go to grocery store, see how many items were there. But the arrangement of these items makes it much easier for us to find those items. Same way, they were looking for some pattern so that we can study large number of elements. See, 118 elements are known to us today. So several attempts were made to classify elements according to their properties and obtain orderly arrangement out of chaos. Then so earliest attempt, it was to classify or it was to group them as metals and non-metals. So this was the earliest attempt. Now let's start and look at the works of different scientists, what they have done, how they classified different elements and how they helped us. So the first arrangement or first such arrangement was that of Dobereiner's Triads. So what is that? See, John Wolfgang Dobereiner, a German chemist, he tried to arrange elements with similar properties into groups. So he took some elements, those properties whose properties were similar. He had identified some groups having 3 elements. So he called these groups as triads. So triads means, so 3 elements were there in each group, so that's why, so those groups he named as triads. So he showed that when 3 elements in a triad were written in order of their increasing atomic masses, the atomic mass of the middle element was roughly the average of the atomic masses of the other 2 elements. So roughly, if we take the average of 2 elements, then the middle one, it will be equal to that mass which we calculated. So it will be roughly equal to that. Let's see how. See, these are the Dobereiner's triads. We can see this one, set 1, set 2 and set 3. First triad, it's calcium, strontium, barium, and their masses are already written here. And second triad, it's lithium, sodium and potassium, and third it is chlorine, bromine and iodine. So what he mentioned, first of all, why he made these triads? Because of their similar properties. Calcium, strontium and barium, their properties are similar, that's why he kept these 3 in one triad. Similarly, lithium, sodium and potassium, their properties are similar, that's why he kept these 3 elements in one triad. And then chlorine, bromine and iodine, their properties are similar, that's why he kept these 3 in one triad. Now what he mentioned, that if we take 3 elements, then the mass of the middle one, this one, it will be equal to the average masses of these 2 elements. So let us find it out also. So it will be equal, or it will be roughly equal, approximately it will be equal to their average. See, average of the masses of calcium and barium. Calcium, its atomic mass is 40 and barium, its atomic mass is 137. So let's take average, 40 plus 137 divided by 2. So on taking average of calcium and barium, we got 88.5. So you can see now this 88.5 is roughly equal to 87.5. So roughly or approximately, or it's near to 87.5. So here that's what he mentioned, that it will be roughly equal to the average of these 2. Let's see for the second triad, lithium. It is 7 is the atomic mass and potassium 39 is the atomic mass. So let's take the average, 7 plus 39 by 2. So we got 23, and 23 you can see the mass of sodium, it is 23. Same way chlorine, bromine and iodine. So we have to take the average mass of chlorine and iodine, which is 35.5 and 127. So let's take 35.5 plus 127 divided by 2. So we will get 81.2, and you can see this 81.2, it is roughly equal to 80. So that's what he mentioned, like atomic mass of the middle element, it will be equal to the average mass of the other 2 elements. So he proved also, you can see in the first one 88.5 we got average mass, which is roughly equal to 87.5. Same way in second triad also 23 we got exactly equal, and in third triad 81.2, which is roughly equal to 80. So other thing apart from the masses, he mentioned that their properties are also similar. If we see this triad, calcium, strontium and barium, see all of these elements, their valency is +2. Calcium also +2, strontium +2 and barium also +2. So they have same valencies. All of these 3 are metals, and their hydroxides are basic in nature. For example, calcium hydroxide, strontium hydroxide and barium hydroxide. So all of their hydroxides, they are basic in nature. So in basic character, in acids, bases and salts, you have already done what are acids and what are bases. So same thing. So their hydroxides are basic in nature. That's how all the 3 elements, they are showing same properties in this triad. So let's discuss the other triad also. So chlorine, bromine and iodine, all of these 3, they are showing valency -1. So their valency is same. all of these are non-metals, all the three are non-metals, and their halides are acidic in nature. Halides means they are compounds with hydrogen like hydrochloride, hydrobromide and hydroiodide. So these are acidic in nature. So this is how these three elements are also showing similar properties. See, he has proved this thing, but again this arrangement, it failed. So why it failed? Let's find it out by studying the demerits or the reasons of failure of Dobereiner's triads. See, at the time when he had given his triads, 56 elements were known at that time, but only he could identify only 3 triads from the elements known at that time. So 3 triads means only 9 elements he could arrange, or he could identify, or he could made arrangement of only 9 elements. See, but the elements which were known at that time, it was 56. So then this was the first major drawback or demerit of his triads. The second one is, even in the same group this law failed, because he was talking about the average atomic mass. So if we take this group of halogens, fluorine, chlorine, bromine and iodine, see, all of these are halogens. So for chlorine, bromine and iodine, he has already shown that the atomic mass of bromine, it's the average atomic mass of chlorine and iodine. But if we take fluorine, chlorine and bromine, see, fluorine, its atomic mass is 19, chlorine, its atomic mass is 35.5 and bromine, its atomic mass is 80. So if we take the average of fluorine and bromine, 19 plus 80 divided by 2, we will get 49.5. And if we compare this average mass with the mass of chlorine, it's a huge difference. It is 35.5, but the average which we got, it is 49.5. So within the same group, see, this law, it failed. So these are the two main drawbacks of Dobereiner's triads. But see, his work also, it inspired lots of other scientists also. So now the second one, or second scientist which gave us the second type of arrangement after Dobereiner's, this Newland. He encouraged, Dobereiner, he encouraged many chemists to correlate the properties of elements with their atomic masses, because the main criteria which he has used was that of atomic mass. So he encouraged many of his contemporaries to work on the same thing. So in 1866, John Newlands, an English scientist, he arranged the then known elements in order of their increasing atomic masses. So then known elements, like we have already talked about, that 56 elements were known at that time. So he arranged those elements in order of their increasing atomic masses. See, all the elements he arranged in order of their increasing atomic masses, not like Dobereiner, because he could arrange only 9 elements. But what Newland done, he arranged all the elements in order of their increasing atomic masses. He started with the element having the lowest atomic mass, so which is hydrogen. He started with hydrogen and ended at thorium, which was the 56th element. So 56 elements means this was the heaviest element, and this hydrogen, it was the lightest element. So he arranged all the elements in this order. He found that every 8th element had properties similar to the first one. So after doing such arrangement, he found that every 8th element, so from wherever we start counting, every 8th element, it was showing the property similar to that of the first element. Since every 8th element was showing, that's why he named this as law of octaves. And since his name is Newland, John Newland, so this is also known as Newland's law of octaves. Octave means like something which is related to 8. So in Newland's octaves, the properties of lithium and sodium were found to be same, as sodium is the 8th element after lithium, and similarly beryllium and magnesium resemble each other because magnesium, it is the 8th element after beryllium. So we'll see how. So before discussing this, see, one very interesting fact or thing I want to share, that Newlands, he was a music lover. What he did, he just correlated music and chemistry. In music, we know we have 7 tunes, whether it is like Western music or traditional music. Everywhere music, it has 7 sounds or 7 tunes, which is sa, re. So he just correlated these two. So if we see the tunes of music, see sa, re, ga, ma, pa, dha, ni. So after ni, this is 7th one. Again we'll start with the first one. So same thing he has done. He just correlated these tunes of music and the elements. See, hydrogen, lithium. So this arrangement he has given. Like if we start from hydrogen, so 1, 2, 3, 4, 5, 6, 7, 8. So fluorine is the 8th element after hydrogen, which means fluorine and hydrogen, their properties resemble each other. Their properties are similar to each other, as fluorine is the 8th element after hydrogen. Now if we start counting from here, see, we can count from anywhere within this arrangement. If we start from lithium, 1, 2, 3, 4, 5, 6, 7, 8. So after lithium, sodium is the 8th element, which means sodium, it will resemble the properties with lithium. So their properties will be same. If we start from beryllium, 1, 2, 3, 4, 5, 6, 7, 8. So after beryllium, magnesium is the 8th element, which means properties of magnesium, it will be similar to beryllium. So you can count from anywhere. So the 8th element, it will have same properties compared to the same properties with the first one. So this is what he has identified, or he has mentioned in his law of octaves. And octave means which is related with 8, and you can always remember that this is, he correlated this thing with music, as music also has 7 sounds. So let's study what are the merits of Newlands law of octaves. See, it was the first time that elements, they were arranged in order of their increasing weight. So first time someone has done something like that, like all the elements he has arranged in order of their increasing weight, and he has given the relation between atomic mass and properties of elements. So this relation, because he has given the properties as per the increasing atomic mass. Lighter elements like lithium, sodium and potassium and beryllium, magnesium and calcium, they were grouped together. So this is also one of the merit. Then he mentioned about periodicity. Periodicity means, he was the first one who mentioned about periodicity of elements. Periodicity means the occurrence of similar properties in elements occupying similar positions in the periodic table. See, that is what after hydrogen we have seen fluorine, which was just below hydrogen. See, similar position fluorine was occupying, and it was resembling the properties also. Like if we talk about lithium, after lithium, just below lithium, sodium was there. So it was in the similar position and it was resembling the properties of lithium. So that is what the meaning of periodicity, that similar properties after occupying similar positions in the periodic table. So he was the first one who mentioned about this. But still he has done so much of work, so much of things, so many elements he has arranged, but still his law, it failed. So why it failed? Let's find it out now. See, it was found that law of octaves was applicable only up to calcium, as after calcium every eighth element did not possess properties similar to that of the first. So it was only applicable till calcium. See, calcium in periodic table, if we see in today's periodic table, its atomic number is 20. So after, and its atomic number is 20 and its atomic mass is 40. See, after atomic mass 40, like, it was not applicable. This law was not applicable. So this was the biggest drawback or limitation of his law. It was assumed by Newlands that only 56 elements existed in nature and no more elements would be discovered in the future. But later on, several new elements were discovered and whose properties did not fit into the law of octaves. See, he just assumed that only 56 elements are known and no other elements would be discovered. So this was also one of the major drawback, because from time to time many new elements they are discovered. You can see also it was 56 that time and now it is 118. So but he assumed that only 56 elements they are existing and no more elements would be discovered. So in order to fit elements into his table, Newlands adjusted two elements in the same slot but also put some unlike elements under the same knot. So he also put two elements. We'll see, I'll show you how. So two elements in the same slot he has put, and some elements he has put like whose properties are also not similar to the previous one. So one of this is cobalt and nickel. He has put these two elements in the same slot and these are placed in same column as fluorine, chlorine and bromine, but their properties are very different from these three. Same way, iron, which resembles with cobalt and nickel, it has been placed far away from these elements. And moreover, like, he thought no more elements would be discovered, but with the discovery of noble gases, the law of octaves, it became irrelevant. Thus, Newlands' law of octaves, it worked well with the lighter elements only. So we'll discuss these three once again by looking at his table. So we have discussed just now, see here hydrogen, fluorine, chlorine, just below this cobalt and nickel. So two elements he has placed in the same slot, and these two elements, their properties are also not similar with these three elements. But if he is arranging these elements, their properties should be similar, but he has done here something, their properties of cobalt and nickel, they are not similar with this, and then also he has placed in the same column. Same way, iron, see, he has mentioned properties of every eighth element, it will be similar to the first one. So if we see iron, its properties will be similar to this element, but the properties of iron, it is similar to cobalt and nickel. So that should be in the same slot, but he has put these elements also in the different slot. And then we were talking about noble gases. If you see today's periodic table, we can see that after hydrogen, helium comes, after fluorine, neon comes, after chlorine, argon comes in the periodic table. And if you write here hydrogen, helium, then every ninth element, see hydrogen, helium 1, 2, then lithium will be third one, 4, 5, 6, 7, 8, 9, fluorine will be ninth element if we add helium here. Then every ninth element will have same properties to the first one, but he has given the law of octaves, that every eighth element, their property is similar to the first one. Same way, if you add after fluorine, if you add neon, then again chlorine will be the ninth element after fluorine. That's why after the discovery of noble gases, the law of octaves, it became completely irrelevant. So this was all about Dobereiner's triads and Newlands' law of octave. Now let us discuss few in-text questions. So these questions are given in between NCERT textbook, and these are blue in color. So related questions we will cover now. So question number 1 is, did Dobereiner's triads also exist in the columns of Newlands octave? compare and find it out. So you just have to see Dobereiner's triads also and the table which Newland has given. Both you have to see and you will find it out that Dobereiner's triad also existed in the columns of Newland's octaves, because the one of the triad is lithium, sodium and potassium, and if we consider lithium as the first element, then sodium is the 8th element, and if we consider sodium as the first element, then potassium is the 8th element. So this is how these two are. Dobereiner's triads also existed in Newland's law of octaves. We can see here. So these are the three triads which Dobereiner has given: lithium, sodium and potassium, chlorine, bromine and iodine, calcium, strontium and barium. So this is Newland's law of octaves. So first triad, if we see lithium, sodium and potassium. So lithium, sodium and potassium. Here we can see this first triad of Dobereiner's. Now let's do question number 2. What were the limitations of Dobereiner's classification? So this thing in detail I have explained. So same thing you have to write here also. Dobereiner could identify only 3 triads from the known elements at that time, and even in the same group this law failed, as we have taken the group of halogens: fluorine, chlorine, bromine and iodine. If we take these 3, fluorine, chlorine and bromine, this law will fail. If we find average mass of fluorine and bromine, we can see their average mass is equal to, or average atomic mass is equal to 49.5, which is not equal to, or which is not closer to 35.5. So within the same group this law failed. So these limitations you can mention here in question number 2. Third one, what were the limitations of Newland's law of octaves? So same thing we have already discussed. Let's discuss it again. It was found that the law of octaves was applicable only up to calcium, as after calcium every 8th element did not possess properties similar to that of first. So we have already discussed this thing. He assumed that only 56 elements they will exist in nature, no new elements would be discovered. Then he put 2 elements in the same slot, cobalt and nickel, and same slot with that of fluorine, chlorine and bromine, and their properties were not similar. Their properties were very different from each other. Then again with iron also same thing he has done. It was resembling the properties with cobalt and nickel, but he has put iron in the different slot. And last, with the discovery of noble gases, this law, it became irrelevant. So this is all about Dobereiner's triads and Newland's law of octaves. Related questions also we have covered. So in this video I will be discussing this much only, and in the next video I will continue with Mendeleev's periodic table. Thank you so much for watching the video. See you in my next one.